Today we're going to do two-way analysis of variance. It's an extension of the one-way analysis of variance, but the notation, the way we talk about it is quite different. There are new things that come up in two-way analysis of variance. Let's start by getting some notation. The properties we're going to talk about are called factors. A factor is a property of interest. I'll make it clear when I give examples, but a factor is just a property of interest, and there are two of these. That's why it's two-way analysis of variance. There are going to be two factors. Then there are levels of the factor. Levels. These are the specific values of that factor. And this is left over from agriculture. By now you probably suspected that what happens in statistics is there's a problem in some field, like agriculture or economics, somewhere. And a statistician sits down and he solves that problem and invents a new technique to do it. And the names he uses to describe the pieces of that technique invariably relate to the field of interest that he's working with. Then that same procedure is used in a totally different field, because it's the arithmetic that the statistician is interested in, and it turns out that that arithmetic is the same in this other field. Well, it's been tradition that the names that were first used are kept. And in this case of two-way analysis of variance, factors are things like fertilizer and irrigation. And levels of a factor are 5 pounds of fertilizer, 10 pounds of fertilizer, 15 pounds of fertilizer. Those are the levels of fertilizer that's used in my experiment. Irrigation, 1 gallon per hour, 2 gallons per minute, 3 gallons per minute, whatever. That's the level of the irrigation used in the system. So there were factors and there were levels of that factor used when we talked about agriculture. But we can use analysis of variance in any field, and the example I'm going to give you here is quite far away from agriculture. Let's say the factors are pickup trucks. That's a factor. And a level of that factor might be Ford, GM, or Toyota. They are 3 levels of pickup truck, like 5 pounds of fertilizer, 10 pounds of fertilizer, 15 pounds of fertilizer. But you can hardly think of them as levels. There's no relation. There's no numerical relation between them. Yet we use the same notation we had before. The levels of the factor. Ford, GM, and Toyota are levels of the factor pickup trucks. Now the next factor in the experiment, we have to have 2 factors in the experiment. The next factor in the experiment might be color. In fact, I haven't got it written down here, but let's say you have to have 2 factors. The next factor is color. All right? Now, what about color? Well, it could be blue, or red, or black. Whoops. Okay? So you can have 3 levels of the factor color. So this is a factor, this is a factor. These are levels of a factor. And when we talk about something that has 2 factors in it, we're talking about what's called a factorial experiment. Now actually a factorial experiment can have more than 2 factors. Statisticians can analyze multi-way factors, but we're going to stick with 2 because all the ingredients that are needed to understand what's going on are inherent in the 2-factor experiment. Each subject that each thing you investigate must be at one level of each factor. That is, we take a measurement. Now the measurement is not a level of a factor. The measurement is not a level of a factor. The measurement is that which is being measured. And it is not a factor, and it is not a level of a factor. And what do I mean by that? What I mean by that is, if you're looking at trucks and colors, you could find a blue Ford, and you have not made a measurement yet. You simply have a subject, that is, one level of each factor. The Ford is a level of the factor pickup truck. Blue is a level of the factor color. And when you say a blue truck, blue Ford, a blue Ford, you are saying that's my experimental unit. Now let's make a measurement. I haven't made a measurement yet. Maybe we'll measure mileage. How many miles per gallon does it get on the average? This would be my measurement on this subject. Okay? So we have a subject on which we take a measurement, but we must have a measurement. The measurement is not a factor, it is not a level, it's something different than the two. Okay? Let's take an example. Here's an example where I have two factors, schools and sex. The schools are agriculture, architecture, arts and science, business, education, English, and human resources. And the sexes are male and female. And now, any person that I have in my survey must be in one of these schools and must be either male or female. And I have 1, 2, 3, 4, I have 10 people from each of 7 schools. I have 70 people in my survey, 35 of which are males, 35 are females. I have 10 people from each school. Now, I have these people. What have I done with them? Well, I gave them an IQ test. And I wrote down the IQ result that I got from each of these 70 exams. And that's my data. Now, this is fake data. Don't go trying to read too much into the data. I made up the data to illustrate certain points. Now, if we take this data and we analyze it, now you can't analyze it by hand. What you're looking for is, this is the within, this is a within something, this is a within, this is a within, this is a within, and the differences all over the place from here to here, from here to here, from here to here, are the betweens. And there's a lot of withins and a lot of betweens, and we really are interested in only 3 things. And you'll see what they are in a moment. Because each measurement can be considered made up of several pieces. One piece being the overall mean. That's common to everybody. Everybody has that much of an IQ, no matter whether they went to school or not. And if they were female or male, it wouldn't matter. They have a certain amount there. Now, superimposed on that average amount is an amount due to the fact that they go to a certain school. People in one school may be higher than average. People in another school might be lower than average. So there's a numerical value which is added or subtracted because of the school. That is, which school, which level of factor A. This is the factor A value, and it's a different amount for each level. Now, this is the factor B amount, which in our example here was sexes. So there's 2 of them. Now, we might be adding something or subtracting something because a person is a male or a female. So that's how we will get a measurement. But there's more to the measurement. Let me skip this for a moment. We'll go to this one. There's an error. Not everybody in the same group, in the same school with the same sex is going to have the exact same IQ. There is an internal within error, experimental error, a natural variability in these measurements. Not explained by the overall average or the fact that they're in arts and sciences or the fact that they're female. It's not explained. This is the variability. But there's another piece. There's another piece. And that piece is called the interaction or the joint effect. It's an effect due to the fact that I'm in a particular level of A and a particular level of B. There's something happening because of a joint effect between them, not just because I'm in A, not just because I'm in B, but because I happen to be in a particular value of A and B. That's called the interaction effect. And the easiest way to explain it is just, let's look at this data. You can see an interaction effect. If I were to think that, let's look at architecture. Look at these IQs up here, male IQs. They're pretty high, at least compared to in this case, the female values. They're pretty low. So you might say, oh, males are smarter than females. They have a higher IQ. Let's look over here at arts and sciences, though. The arts and sciences male IQs for this data, remember this is made-up data, don't go jumping on it. This is low compared to the very high IQs of the female arts and science. So you can't say, if you said males are smarter than females, here you'd have to say males are dumber than females. And how does that jive? What we're trying to do is say, well, males have something that we're adding, females have something that we're adding and subtracting, and there's something due to each school, but there's something more. There's an interaction here. In this case, male architects do well above average. Female architects do below average. Male arts and sciences do below average, and female arts and sciences do above average. So it's not only what school you're in, but also what sex you are combined. Now, if all the males were higher than all the females generally, or vice versa, we'd have an effect due to sex. If all of one school was generally higher than all of another school, we'd have an effect. But if we have an interaction like this, we have an effect due to that. And that's why we have that term in the model, the AB term. This is the interaction term. We might have an A effect, we might have a B effect, we might also have an interaction effect. So there are three ways that we can not have an overall mean. The null hypothesis is that none of these are there. All we have is an overall mean. Everybody's the same except for experimental error. Everybody's the same except for experimental error. In that case, there is no school effect, there's no sex effect, there's no interaction effect. And we have to test this. We have to say, is there significant evidence to say there's a school effect? Is there significant evidence to say there's a sex effect? Is there a significant effect enough for us to be able to say there is an interaction effect? And we do this by checking each of these things separately. These are separate tests made by the analysis of variance program, the two-way analysis of variance program. So let's run it, see what happens. Here's the output using Minitab again. Run this and I say ANOVA, and I gave it, instead of a column, I'm calling it IQ, which is a quote in quotes because it's the name of something. It's really in a column. And I say schools, which is the name of another column, and sex is the name of another column. I haven't shown you the data, but the data will look a lot like the data you saw on the input. And it just lists a bunch of output. Now notice what we have here. We have error. Remember, the error is the within. That's the within. This is the school effect. We call it the A effect. This is the sexes effect. And this is the interaction, the schools times sexes effect. And here's the degrees of freedom associated with them. Let's go to the mean squares. The within mean square is 48. The mean square for schools isn't much bigger. It's only 1.17 times as big. The sexes mean square is significantly bigger. Well, it's bigger. It's 4.6 times bigger. And the interaction is tremendous. It's 9.62 times as big. That's very big. Well, let's look at what the p-values. This is the important thing. What are the p-values? The p-value for schools is 0.33. Can I reject at the 10% level? No, because 10% is not bigger than 0.3. In fact, nothing is bigger than 10, 5, 1. They're all smaller. I must fail to reject at any level. Fail to reject at 10%, fail to reject at the 5%, fail to reject at the 1%. So what I have to say is that I don't believe there is a school effect. It means schools don't differ. Schools really behave the same way. There's no difference in IQ between the schools for this data. Now let's look at the sexes. 0.036. If I were to make a 0.1 level test, a 10% level test, 10% is bigger. 0.1 is bigger than 0.03, and therefore I reject the hypothesis that sexes don't count, that there's no difference between sexes. In other words, I've demonstrated at the 10% level that there is a difference between the sexes. Someone says make a 5% level test. 5% is bigger than this. 0.5 is bigger than 0.3. I can reject the hypothesis that there's no sex effect and say, yes, there is a difference between the sexes. How about the 0.1 level, the 1% level? I'd have to fail to reject. I say, well, there's not enough evidence to show that the sexes differ. Now, how about interaction? 0. 0.1 is bigger, 0.05 is bigger, anything is bigger than this, so anything will reject. I reject at any level that there's no interaction. Clearly, with this data, there's an interaction. We saw it with the naked eye. There is an interaction there. And it's so obvious, it was obvious to the naked eye, that the computer found it without any error and says, hey, there's no way. Now let's do that once again so that we understand p-values. Meaning of the output. Schools, 0.3. Alpha equal 0.1, alpha equal 0.05, alpha equal 0.01. 0.1 is bigger than that, is not bigger than that, fail to reject. 0.05 is not bigger, fail to reject. 0.01 is not bigger, fail to reject. In fact, when you see something that big, you see anything around 0.3 or higher, we say fail to reject at any reasonable level. And that's all. You don't even have to ask the boss man what level he wants you to make the test. You just say, when he comes in the room, you'll have to fail to reject at any reasonable level, because he's not going to ask you a level 0.4. That doesn't make any sense at all. Okay? How about the others? 0.036. 0.036. 0.1 is bigger than it, so I can reject 10% level. 0.05 is bigger, I can reject at the 5% level. So reject at the 10% and 5% levels, but fail to reject at the 1% level. So here you really have to wait for him to tell you what level he wants, or you can just spout that at him, knowing he's going to pick one of these three, and it would be pretty informative to let him know that he would reject at those levels, but fail to reject at that one. Now when you see a 0, you simply say reject at any level, because no matter what they said, alpha of 0.1, alpha of 0.05, alpha of 0.01, and if they wanted something else they said, that's fine too. No matter what they say, it's bigger than 0, and so you reject at any reasonable level. Okay, let's now see what we had. Remember, we had high here, low here, high here. Well, I'm going to interchange these two. So put this column over here, that column over here. Then we won't have the effect anymore that there's at least we're going to reduce the interaction effect. There may be other interactions effect that we can't see with the naked eye, but if we do that, there's very little that we can see in this thing with the naked eye. We will need the computer to tell us what's going on. Okay? So interchange this and this. However, I will let you note something, that when you do interchange this and this, all these numbers get to be very high, and all these numbers get to be very low. Or people don't like that in this class. Let's interchange these two. Let's put all the high ones here and the low ones here. Then all of architecture is very low, and all of arts and sciences is very high. That makes the more people happy. But remember, this is fake data. This data really is not real. It's just made up in order to show the points we're making. Now let's do the analysis of variance with this data. We're again only interested in the p-values. This is the p-values for schools. This is the p-values for sexes. This is the p-values for the interaction. Notice that the ratio before was 9, now it's only 7 or 8. Things have changed. And now we have a very small p-value for schools. Before, we couldn't reject the hypothesis at any level that schools had an effect, and now it's clear at the 10% level, at the 5% level, even at the 1% level, we can reject the hypothesis that the schools are the same. In other words, the computer is telling us there's no question in its mind that schools differ in IQ ability. People going to different schools, different IQ ability. How about sexes? Here it's saying there's absolutely no evidence whatsoever that the sexes differ. It says, at any level you like, 0.1, 0.01, 0.05, or whatever, there is no evidence, because you cannot get a number bigger than that the sexes differ. So we're saying sexes do not differ. The null hypothesis says the sexes are the same. We agree with them. The sexes are the same. How about interaction? For some strange reason, there's still a very high interaction. We're rejecting the hypothesis at any level that there's no interaction. Schools and sexes seem to interact somehow. We left that stuff, still got left in there for some reason. Okay, let's go through it slowly. 0.005, reject at any reasonable level, because any level is bigger than 0.005. 0.1 is bigger, 0.05 is bigger, 0.01 is bigger. So reject at any reasonable level. Schools they differ. Null hypothesis that schools don't differ in IQ. People going to arts and sciences, well, that's the same as people going to architecture, and we say with this data, that's not the case. There's evidence to show that IQs differ from school to school. How about sexes? The males and females differ in IQ ability. We've already filtered out the differences between the schools. Now, ignoring the differences between the schools, but only seeing what component of the difference in IQs that are there is caused by the sexes, we say there's absolutely no reason to believe that sexes differ. There's no evidence there whatsoever. We fail to reject at any reasonable level that the sexes differ. No evidence to say the sexes differ in IQ. But is there an interaction? Do some males do better in some school and some females do better in other schools? And the answer to that is yes, we believe that highly. We reject the hypothesis that schools and sexes do not interact, that they're all the same. It's not the case. In some cases, males do better in some schools than females. In other schools, females do better. That's what this is telling us. We're rejecting the hypothesis that there's no relation here and that they're all the same. They're not. We reject that hypothesis. Okay? That's a two-way ANOVA. And of course, there can be more than two-way. We could have pickup trucks that are blue and also use high-test gas. So we could have three factors. We could have people going to school, different schools, different sexes, and different levels, freshman, sophomore, junior, senior. So we would have three factors in that experiment, and then check IQ. It would be a much more complicated experiment. The computer could do it just as quickly. However, we're not going to try analyzing that here. If we get through two-way, we'll be pretty happy. See you next time.